Hi, about
no, I give a 5 minutes to go through the exercise.
Oh, yeah, please say it again because I think they didn't hear you.
Okay, thank you. All right, guys, you've got this 5 minutes to go through this exercise to finish up the exercise that we started yesterday. Please go through it so that we can do it together. Thank you. 5 minutes to go through the exercise.
Oh, yeah, please say it again because I think they didn't hear you.
Okay, thank you. All right, guys, you've got this 5 minutes to go through this exercise to finish up the exercise that we started yesterday. Please go through it so that we can do it together. Thank you. Okay, those of us who would like to raise up their hold your question, note your question, rather text me, I will respond to the text. All right, those who are raising their hands, please, can you text me so that we can chat? All right, the 5 minutes is over now. Let's just go through the exercise. I think yesterday we managed to do 2.1 together, the free body diagram. Let's just go to the solution quickly. In the solution there, we said you will have the frictional force, the weight, the normal force, and the applied force F. And then I've said to you, you can also represent this applied force, resolve it into its component. That is the vertical component and the horizontal component. Right, and we have also mentioned the acceptable labels. The normal can be represented by N or normal force or Fn. The frictional kinetic frictional force can be represented by Fk or just frictional force. And then you can also, the applied force, you can represent it with F applied. And then the weight, you can represent it as W or write it in full weight or Fg or gravitational force. Right. And then I've also mentioned that the force F may be represented by both Fx, the horizontal component, and the vertical component there. Right. So now, ask about the to state Newton's first law of motion in weights. So the law will be as follows. A body will remain in its state of rest or motion at a constant velocity unless a non-zero resultant or net force acts on it. Right. The other question was to um, calculate the magnitude of force F, this force, the normal and the frictional force. Now, the expected response there was, we know that F net equals to MA, but the forces that are acting horizontal here along the horizontal are F, the applied force, but it is its component, which is F cos theta, that is the horizontal component of the applied force, minus the frictional force, because the frictional force is acting in an opposite direction, equals to MA. Then we know that then we can say we know that this object is moving at a constant velocity. Therefore, it means acceleration is zero. We can say MA becomes zero. And then we know that this will be our F multiplied by cos theta, which is now giving us the horizontal component of this particular force. So we know that cos 20 is 0.94 multiplied by F, and then mu K, we're giving it to be 0.4. Now, this part here, it is representing the normal force. So where does it come from? It is coming from here. We know that from our diagram. Let's go back to our free body diagram. So in here, you can see that the weight Fg is equals to Fy plus normal. So let's go to our calculation. Fg is it is Fy, which is sine theta, and then plus normal. So Fg, the weight is mg, and we know that this will be Fn, and then this is F sine 20. Now we know that this will be given by M will be 15, G is 9.8, and then they will give you 490, and then sine theta will be 0.34. So what we are doing, we want to remain with Fn. So we keep Fn and we transpose this to be 490 minus 0.34 multiplied by F. So we substitute this where we are having Fn, we substitute 490 minus 0.34 here. And then we solve for F, and then we get our F to be 182,16 newtons. Then we're also asked to determine Fn, which is the normal force. So now from this equation here, we can rewrite it here to say Fg equals to normal force plus the y component of the force, which is F sine theta. Then we can say this, you can write it in either of this form. We know that this Fg is mg, and then this is the normal Fn, and then plus F sine theta. So from this, we know that this will, M will be 50, and then G will be 9.8, and then this is our Fn, and then we have just calculated our F to be 182,16, which is this one. We substitute it, and then sine theta, it will be sine 20 degrees. Then we can be in a position to calculate Fn, and your answer should be 427,70. Right. Here, what I've omitted, it should be 182,16 multiplied by sine 20 is what should be added here. And then that should be subtracted from 490 to get Fn. Now, we are also accepting the range. Remember, if you had rounded off earlier, you should be having 428. So this answer will also be acceptable. Right. We continue to look for the frictional force. We know the frictional force is equals to mu k multiplied by the normal force. So the frictional force here will be 0,4 multiplied by 427,7. Then, which is the normal force? We substitute the normal force here, and this is mu k, which is given, and we get our frictional force to be 171,1. But we are, because of rounding off, we can accept up to 171,2. Now, the other question that was asked was, give a reason why the block will move slower than before. Now, we are saying the same block, the same constant force F is now applied to the block over the same rough horizontal surface as before, but now in a direction shown below. Now, instead of this force pulling, is now pushing. So let's see the reason why the block will move slower. Now, remember now the normal force will increase because instead of this force, okay, in here, and instead of this force, the vertical component of the applied force going up is now going down. So it will increase the normal force, thus increasing the frictional force and making it very difficult to move the object forward because the frictional force would have increased. Right. So I hope you managed to get something from this exercise. We have benefited. And then let's carry on with today's lesson. Today we'll be looking at chemical bonds, and then let's carry on. So we'll also be looking at molecular shape as predicted by valency shell electron pair repulsion, which is VSER theory. All right, we'll be looking at the bond length and bond energy. I don't think we'll have time to look at intermolecular forces. That will be our next lesson. So we'll also later on we'll look at chemistry of water. So that is the sections that we will be treating later. But these last two we won't be in a position to treat them today, but we'll treat the first three. Right. So here it is under atomic combination and molecular structure. So this is what you should be knowing at the end of this lesson. So let's look at chemical bonds. We are defining chemical bond as a mutual attraction between two atoms resulting from simultaneous attraction between their nuclear and the outer electrons. So that is chemical bond. You are having two atoms that are simultaneously attracting each other from either their nucleus and their outer electrons. So now with both their nucleus and outer electrons. So we can see that the energy of combined, if we are talking about chemical bonding, so one can ask himself a question, why is it important that we are having chemical bonding? The energy of combined atom is lower than individual atom. This will result in higher stability. So meaning that the atoms that are bonded together will be more stable than individual atoms. So let's just go through this particular diagram here. I think I've taken it from Chem Libertex. And then from here, what we can see is that if we are having two atoms here, their energies will be higher. But as they are coming together, during bonding, energy will be given off. as you can see here, energy is given off during bonding. As they are coming together and bonding, energy will be given off. And then as they come more and more and more closer, they end up repelling each other. So this side will be repulsion section. So now let's see, if this, say you are having two hydrogen atoms that have bonded together, if they have to separate, going their own way, what will happen is that you will need to absorb, to supply energy to break the bonds. So remember, when bonds are being formed, as is needed to break one mole of its molecule into separate atoms. So bond energy of a compound is the energy needed to break 1 mole of its molecules into separate atoms. So, and what is bond length? Bond length is the average distance between nuclei of two bonded atoms. So now let's go back to our diagram quickly. So the distance between this nuclei would then be bond length. And then the energy that is released when bonds are formed is then called bond energy. Right. Bonds with shorter bond length will require more energy to break than bonds with longer length. So meaning that bonds that are shorter will be stronger than those that are longer. So longer bond, compounds with longer bond length will be weaker in terms of the amount of energy needed to break the bonds. So if the force of attraction between two atoms is strong, the nuclei will become closer together, resulting in a shorter bond length. So also, if the forces of attraction is strong, it means the bond length will be stronger. So bond length between larger atoms is longer than the bond length between smaller atoms. So remember this. So for instance, if you are having a bond between, let's say, carbon and hydrogen, it will be, the bond length will be smaller than the bond between carbon and nitrogen, for instance. So bond strength increases as number of bonds between the atoms increases. That is, triple bonds will be stronger than double bonds, and double bonds will in turn be stronger than single bonds. Right, let's look at what we call Lewis dot diagram. So what is this Lewis dot diagram? It's a structural formula in which valency electrons are represented by dots or crosses. Right, it is also known as electron dot formula or Lewis formula or electron diagram. Right, let's draw Lewis diagram for the following elements. Hydrogen, you can see it's already drawn there. It is because it is element number one, it is in group one, it is having one valency electron. I'll talk about valency later on, but as valency is basically electrons in the outer energy level. So in this instance, you can see that it is having one. So it is this electron in the outer energy, just one dot. The electron is represented by dot. And then nitrogen, because it is in group 5, it is represented by this 5. We do this paired electrons and this 3 electrons that are unpaired. Right, same applies to oxygen. It is in group 6, it will have 6 electrons on the outer energy level, or it will have 6 valency electrons. Same applies to chlorine, it will have 2, 4, 6, 7, because it is in group 7, or normally it's called group 17 if we are to include transitional metals. Right, and then your neon here will be having all the 8 electrons on its outer energy level because it is on group 8 or group 0. Right, let's carry on. We have said that what are valency electrons? So valency electrons are electrons on the highest energy level of an atom. So now, what is a covalent bond? Covalent bond, it is a bond that involves sharing of electrons between 2 atoms to form a molecule. For instance, let's consider hydrogen. Hydrogen is in a position to bond with another hydrogen atom to form hydrogen molecule, which is diatomic molecule. But helium does not. Why is that the case? Because all the valency, the most outer energy level is completely filled. So that is why it will not form, it is not reactive. Right, and then we want to define a molecule. A molecule is a group of 2 or more atoms covalently bonded and that function or behave as a unit. Right. And you can also use a periodic table to determine the number of valency electrons. That is, you can go to the periodic table and see in which group is an atom so that you can be an element so that you can know its valency electrons. Right. Bonding pair of electron is a pair of electron that is shared between 2 atoms in a covalent bond. Right, and then lone pair of electron is a pair of electron in a valency shell of an atom that is not shared with other atoms. So they are just there, they are lone pair. So let's just quickly go through the rules for covalent bonding. So in here, different atom, each with unpaired valency electron, can share these electrons to form a chemical bond. For instance, two hydrogen atoms can form hydrogen molecule by sharing a electron pair, meaning that each of the hydrogen will be coming with 1 and the other one with 1, and then they will bond together to form a hydrogen molecule. And then different atoms with paired electrons called lone pairs cannot share these 4 electrons and cannot form a chemical bond. That is normally under normal circumstances, you will not have a bond between the helium atoms, right? So the other thing is that if the outer energy level is completely filled, you will not have a bonding. That is, those atoms with outer energy level that is completely filled will not bond. Right. Different atoms with unpaired valence electrons can share these electrons and form a chemical bond for each electron pair shared. So two atoms can form multiple bonds between them. For instance, a oxygen molecule can be formed by two oxygen atoms that can have double bonds, right? And then atoms with empty valency shell can share a lone pair of electrons from the other atom to form coordinate or dative bond. For instance, you will realize that oxonium ion, ammonium ion, this you are having hydrogen, which is having an empty hydrogen ion, which is having an empty valency share, coming and sharing the lone pair of ammonia molecule to form ammonium ion. Ammonia molecule to form ammonium ion. And so is the other hydrogen can join the water molecule and then share the lone pairs of oxygen to form oxonium ion or hydronium ion. So this is what we call dative bonding. We'll deal with that at a later stage. Right. If we are having chemical, if we are to draw the Lewis diagram, given the formula and using electron configuration for simple molecules. So let's see, for hydrogen, this will be the Lewis diagram. And then for fluorine, this will be the Lewis diagram. So around each of, for fluorine molecule, you will see that around each of the fluorine atoms, there will be 8 electrons. So it's 2, 4, 6, 8. And then around this one is also 2, 4, 6, 8. And these 2 pairs of electrons will be shared between the 2 atoms. All right, the same applies to water molecules. Water molecule. It is formed by 2 hydrogen atoms and 1 oxygen atom. So around the oxygen atom is 2, 4, 6, 8. But these 2 pairs have been shared with, each has been shared with the hydrogen atom and has been shared with a hydrogen atom. And around each and every hydrogen atom, there are 2 pairs. So this molecule is very stable, is stable. Right. So let's consider OF2. So here it is, you can see that there are 2 fluorine atoms and then 1 oxygen atom. Around it, the oxygen atom is 2, 4, 6, 8 electrons. And around each of the fluorine is 2, 4, 6, 8. And then around each is 2, 4, 6, 8. So the same thing can be done with the this molecule over here. Just what you need to ensure is that around each of this, you look at the group, like your hydrogen, it is in group 1. So it will need a maximum of 2 electrons in its outer energy shell. So you can see that there are 2 electrons around the hydrogen. And for oxygen, it must be 8. The same applies to chlorine. Right, let's look at, this is how the Lewis structure for nitrogen will look like. Right, oxygen molecule will look like this, and then the same applies to a hydrogen cyanide. Right, dative, let's deal with dative covalent bond. It's a covalent bond between 2 atoms where one of the atoms provide electrons that form a bond. So remember, we have said that in here you need one of the atoms must be having lone pairs And then one other atom that is coming must be having an empty shell. So we have talked about oxygen and also hydrogen as an example of that, or nitrogen and hydrogen as an example of that. So dative bond is also called coordinate bond. And let's just do the example. You'll have hydrogen combining with ammonia to form ammonium ion. And then this one is having an empty shell because it has lost one of its electrons. So it comes and shares this lone pair of electrons to form ammonium ion. So hydrogen will also do that with water. So hydrogen will come to share this. Oxygen will then share this lone pair with hydrogen to form oxonium or hydronium ion. Right, let's deal with predict molecular shape using the valency shell electron repulsion theory, or what is known as VSEPR theory. So what are the major principles underpinning this theory? It is that molecular shape is determined by repulsion between the electron pair present in the valency shell of the central atom. So you will see we will be applying these principles as we go on. So the number of electron pairs around the central atoms can be determined by writing the Lewis structure of a molecule. So the shape of a molecule depends on the number of bonding electron groups or atom bonded to the central atom and the number of lone pairs on the central atom. And A is normally used to represent the central atom and X is normally used to represent the terminal atoms. So there are 5 ideal shapes found when there is no lone pairs on central atoms. That is only bonded pairs. Right, let's just look at this. This theory, that is valency shell electron pair repulsion theory, can be used to classify given molecules as one of the 5 ideal molecular shape by finding the number of atoms to the bonded to the central atom in a molecule where there are no lone pairs on the central atoms. So here in this case, we are taking when there is no lone pairs on the central atom. So the first type of molecular shape will be linear shape. So your carbon dioxide will be a linear shaped molecule, and your beryllium chloride will be a linear molecule, and also your ethane molecules will be a linear molecule. Your ethane will be a linear molecule. And then now the next shape, it is what we call, when we are having 3 atoms. So this will give you a trigonal plane, and then it is represent, the general formula is AX3. So this is boron fluoride is an example of a trigonal planar. So let's look at when there are 4 atoms, you'll have tetrahedral molecule. An example of them will be carbon tetrachloride and methane. Right, the formula are there. And then you can also have what we call trigonal bipyramidal. An example of them, it is PCl5. And then this is the shape, trigonal bipyramidal. And then also if there are 6 atoms, you will have octahedral shape. So these are the 5 main shapes of molecules. So remember, we have said it's linear, where there are 2 atoms, and then that is 2 atoms attached to the central atom. Then you've got, if there are 3 atoms attached to the central atom, you will have trigonal planar. When there are 4 atoms attached to the central atom, you will have tetrahedral. And then when there are 5 atoms attached to the central atom, we will have bipyramidal shape. And then finally, if there are 6 atoms attached to the central atom, we will have octahedral shape. Right. Now, let's look at the concept of electronegativity. Electronegativity is a measure of tendency of an atom or in a molecule to attract bonding electron. So we will also have non-polar covalent bond. This one is a bond in which electron density is shared equally between the bonded atoms because they will be having the same electronegativity. So we'll also have polar covalent bond. In here, you'll have that the electron density will be unequally shared between the atom. For instance, in water molecule, you'll find that oxygen is more electronegative than hydrogen. So electron density will be around the oxygen atom. So with electronegativity difference that is greater than 2, electron transfer will take 2.1, sorry, electron transfer will take place and the bond will be ionic. If the 2 bonding atoms are having the difference in electronegativity that is greater than 2.1, you will have electron transfer and that will be resulting in ionic bonding. So ionic bonding will be simply an electrostatic bond between 2 ions formed through transfer of 1 or more electrons. Right, let's look at electronegativity and polarity. With electronegativity that is greater than 1, the bond will be polar covalent bond. And then with electronegativity different less than 1, you will have a very weakly polar bond, polar covalent bond. And then when the electronegativity difference is 0, then you will have a non-polar covalent bond. And then the character of a bond varies purely on covalent, to most of the pure ionic compound. That is, pure covalent bond will have electronegative difference of 0, and then ionic can be even greater than 3. So they will differ from one molecule to the other. So the above difference in electronegativity is only the guide. Many bonds will have ionic, both ionic and covalent bond character in nature. All right, polar bonds do not always lead to polar molecules. You might find that one side is polar and the other, the polarity might cancel out each other and resulting in a non-polar molecule. So let's try to do some exercises. I will be giving you some 5 or so minutes to do the following exercise, and then we will do the solutions together. Okay, let's do this activity and then we'll do the solutions together.